Hello again. In this video, we're going to take a look at one-to-one functions and inverse functions. So before we move on to our next couple of elementary functions that we want to take a look at, we needed to discuss what composite functions are and then what one-to-one and inverse functions are. So today we're going to take a look at one-to-one functions and inverse functions. So let's start with what an inverse function is. So we're going to skip this first part for just a sec, and right below this, I've got an example of a function and its inverse. I just want to kind of play around with this first before we do anything else. So I give us this linear function, f of x equals x plus 4. So every input, you add 4 to it, and it gives you the output. So it's definitely a function of x, because for every x you plug in, you'll get a unique y back out. So every x you plug in, you get x plus 4 back out. So for every x, there's exactly one and only one output, f of x. Now I'm claiming that x minus 4 is the inverse function. And you'll see that it's denoted with this little -1 in the superscript position. Now I'm claiming that, so you don't have to believe me. I'm just saying that it is. Then hopefully by the end of this video, you'll sort of, maybe, possibly believe that they are inverses of each other. Now let's see why I claim that they are inverses. Let's see what one does for the other one. Well, let's say I take x equals 1 from the domain. Now this is a linear polynomial, so we know that the domain's all real numbers, but I'm just going to plug in a few x values. So let's say I plug in x equals 1, an integer. Let's just plug in this integer. If I plug in 1, it adds 4 to it to output 5. That's what the function does. It adds 4 to the input. So if I plug in 2, it outputs 6. If I plug in 3, it outputs 7. If I plug in 4, and if I plug in 5. So it just simply adds 4 to the input. That's what that function does. Well, I claim that this is the inverse of that function. Now, what do I mean by that? Well, in mathematics, when we say inverse, we usually mean the very first encounter you have with it are when you learn the 4 kind of main operations: addition, subtraction, multiplication, and division. You learn later that subtraction is just the addition of the opposite, and that you learn division is just simply multiplication by the reciprocal. But there's more going on there. You have inverse operations. So for example, addition and subtraction are inverse operations. One undoes the other one. So for example, if I were to take 10 and add 8, I would get 18. But the question is, what if I didn't want that 18? What if I wanted to go back to the 10 that I started with? So I've got my output 18. I'd have to subtract 8 to get back to 10, which is where I started. So addition and subtraction are, we say, are inverse operations. They can undo each other. So if I add a number and I go, whoops, I need to go back to where I started, I can subtract to go back where I started. Or if I subtract something to start with, I can add a number to go back to what I started with. So we learn lots of different inverse operations. For example, if you square a number, so 5 squared is 25, and you say, whoa, 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 I want to go back to the 5 that I started with. I screwed up. I want to take my 25 and I want to somehow change it back into the 5 that I started with. We had the idea of a root. I could do the principal square root of 25, which is 5, and that's what I started with, right? I started with 5 and I squared it, and the output was 25. But if I want to go back to the 5 that I started with, I've got this inverse operation of a root that takes me back to the 5 that I started with. So the idea of an inverse is that you have an input, a function is applied to it and gives you an output. So I take 1, I plug it in, the output is 5. But what if I want to return back to the input of 1? Hopefully there's an inverse function that will do that. So let's see. So I take this 1 right here, I plug it into the function, 1, 1, it outputs 5, it outputs this 5, right? That's how we get the 5. So what if I want to undo that? What if I want to return back to this 1 that I started with, my input? Here's how we can do that. We can do that with what's called an inverse function. So I take the output, I take the result I just got, and I input it into the inverse. So I'm going to take 5 and plug it in here. So 5 minus 4 is 1. And my output, 1, is exactly what I started with over here. So basically, this function undoes what this function did to it. So I applied a function, it gave me an output. And I go, uh-oh, I don't want that. I want to go back to the original thing I started with, my input. The inverse function would swoop in, do its magic, and output the original input. So again, let's think through that process one more time. I take an input like 2, I dump it in, 2 plus 4 is 6. Now let's say, so I've got this output, I've got this 6, and it's like, oh man, I've got this 6, but I want to return it back to the 2 that I started with. So I'm going to take this 6 and I'm going to dump it into the inverse. 6 minus 4 is 2, and 2 is exactly what I started with. So you begin with an x, it outputs a y. You begin with an x, it outputs a y, or f of x, or whatever the name of your function is. You take that y, use it as the input for the inverse, and it's going to output a y that was actually the x you started with. So if we were to do this all the way through, the output is 7, plug 7 into the inverse, I get 3, which is what I started with. Output is 8, plug it in, I get 4. Output is 9, plug it into the inverse, I get 5. So if we look closely, on the original function, I had the coordinate 1, 5, but on the inverse, I have the coordinate 5, 1. I had 2, 6 over here, but on the inverse, it's 6, 2. Over here, it's 3, 7, but over here, it's 7, 3. Here is 4, 8. Here's 8, 4. So as you can see pretty clearly with this example, all of my inputs on the original are the outputs on the inverse. And then on the other hand, all the outputs of the original become the inputs on the inverse. So x's become y's, right? Like these are x's, these are y's. X's become y values and y's become x's. So the domain and the range change places. So these are all values from the domain. These are domain values. But over here, those are range values. So a function in its inverse, what it does, when you compare the ordered pairs, you see that domain values become range values and range values become domain values because x's and y's change place. So back to this original question, what's the relationship between ordered pairs of a function f and its inverse? Well, if AB is a coordinate on function f, or I should say, let's be specific, is a coordinate on the graph of function f, then as we just saw, BA is a coordinate on the graph of its inverse. So this shows that the domain of f becomes the range of its inverse, And the range of f becomes the domain of its inverse. So this is a big deal. This is going to basically permeate everything we do today. So when you have a function and its inverse, all the inputs of the original function, they end up being outputs on the inverse. And all the outputs of the original function become inputs on its inverse. So if AB is a coordinate on the graph of function f, then you reverse those. BA is a coordinate on the graph of its inverse. And then we showed an example of that here. But of course, we're gonna dive deeper into that. So we're going to define what it means to be an inverse function. So we're going to let f and g be functions of x. If f of g of x, so a composite function, if f of g of x is equal to x for every x value in the domain of g, and if g of f of x equals x for every x value in the domain of f, then f and g are inverses of each other, and we can write that f is the inverse of g, or if you prefer, you could say g is the inverse of f, because they're inverses of each other, so it kind of depends on how you want to write it. So let's see if this definition agrees with what we saw earlier in our example of our two linear functions that are inverses of each other. So very symbol heavy, so we gotta follow the symbols. So if I write this, what is this saying? Let's walk through what these symbols are saying. It's saying that this is an input, and you input it into G. So input X into G. Then you get back G of X. So G of X is the output. So you take X, you plug it into G, and then you get G of X. That's the output. But look what we do with it now. Then G of X is the input for function f. So basically, let's walk through that again. You take a number x from the domain of G, you plug it into G, it gives you back G of X, an output. But that output now becomes the input for the other function f. So you plug it in, and let's see what we get. If the output is x, so the output of f of g of x, well, oops, I said output and didn't write the word output. So x is the output of f of g of x. Okay, but look where we started. We started by plugging in x. Remember what they're supposed to do. Two functions that are inverses of each other, they're supposed to undo each other. So again, you got to walk yourself through. There's a lot going on with these symbols. You start with a number x. You're starting with an x. So imagine you're holding a number in your hands, a very specific number. Okay, we got a number. We plug it into g. G does something to it. It gives you back g of x. So now you're holding a different number. You plug that into the inverse f. It applies its definition to it. And if it returns back to you x, which is what you started with, then those must be inverses of each other, right? They undid each other. So again, if you got to go back to the example to see a specific one, go for it. You start with an x. Okay, so here, we'll do it over here. No, it doesn't matter. So you start with an x. So you start with x equals 1. You plug it into the function. It gives you back an output, 5. But then you take that number, 5, you plug it into the inverse, it gives you back what you started with, which was 1. And that's what this definition is saying. In symbols, though, it's saying you start with an x, you plug it into a function, it does its thing, the output becomes the input of another function, and then when it does its thing, if it gives you back x, which is what you started with, then they're inverses of each other. Except, I'm being a little loose here, to be true inverses of each other, it shouldn't matter which one you plug it into first. So that's why this sentence is so important. If f of g of x equals x and if g of f of x equals x. In other words, it should not matter which one you plug it into first and which one you plug it into second. They should both undo the other one. So both have to be true. So let's see that right here. First example, which of the following functions is the inverse of this function f, which is the function is 5 over x minus 2. 5 over x minus 2. Well, let's see. Let's see which one's going to be the inverse. So if I take g and I plug it into f, let's see what happens. If they're inverses, it should just give me x. It should just simplify to x. So if I take this function g and plug it into f, let's see what we get. This is why we studied composite functions before this, because I'm now going to plug g into f, multiply the top and bottom by 5. So if I plug g into f, it returns back to me 25 divided by x minus 12. Well, it didn't return back to me x. So by plugging g into f, it didn't give me back what I started with. It didn't give me back x. It gives me back 25 over x minus 12. So g is not the inverse of f. Okay, all's not lost. Let's go plug in, let's go do h and see what happens there. So if I plug in h to f, let's see what we get. We have 5 over, clean that up, 2 minus 2 is 0. Then I get 5 times x over 5, so I get x. Ooh, that's a good sign. So when I plugged h into f, it returned back to me x. The output is just simply x, which is what I started with in the first place. That's a good sign. But that doesn't mean they're inverses of each other. They're only inverses if I can reverse it and get the same thing. So what if I plug f into h? So let's see what happens there. So I'm going to plug in f to function h. So then I'm going to get, well, what am I going to get? Aha, I get x. So no matter which one I plug into the other one, no matter which one's the inner function, they both return back to me the input x. So right here, these two pieces of information tell me that f and h are inverses of each other. In other words, I now can write, if I want to, I can now write if f of x is 5 over x minus 2, then its inverse, which we use f with a little -1 in the superscript, its inverse is 5 over x plus 2. Now let's say, let's say you're like, well, wait a minute, what about h? Why not use h? You could say if h is 5 over x plus 2, then its inverse, h with a little -1, is 5 over x plus 2. So like, or x minus 2. You could do the same thing. So like, or, right? So or, you could say if h, let's just say you prefer to use h as the original function, then its inverse is this. So it doesn't matter. You got a choice at that point. You've got a choice. So all this examples is meant to show you is what we mean by with that definition of inverses. How would I know? How would I prove two things are inverses of each other? So this example illustrates how to prove two functions are inverses of one another. That's what this example is doing. So let's say you've got two functions and you're like, I think they're inverses. Okay, well, here's how you can show that they're inverses. All right, so what about their graphs? So surely, there's got to be something unique about their graphs, right? If they're inverses of each other and their coordinates are just flipped, what's that mean? So turns out, and we'll see an example of this. Matter of fact, why don't we do the example first, and then we can answer that question there. That might actually make more sense. So let's do this example first. So let's sketch y equals x squared where x can't be negative. Let's do that. I'll do that one in blue. Do that one in blue. So it's got a restricted domain. X can't be negative. So it's got a restricted domain. Let's graph it. So it starts at 0. It's just our squaring function, so it goes through 1, 1, and 2, 4. So it's just going to look like this. So that's f. And then its inverse, principal squared of x. So again, I'm claiming that this is the inverse. You don't have to believe me. By the end though, we'll see how you could know that was the inverse. That does not have a restricted domain. We get to use its entire domain. So its entire domain is the same as the other one. It can't allow negative numbers. So it's going to be 0, 0, 1, 1, and 4, 2. So it's going to look like this. That's the inverse. Well, that's it. Now that I see that, we can, I'm going to, just because I can, I'm going to blow this up and make it just a little bit bigger so you guys can see it. Oops. Said I was going to do that and then did not. So let's try that again. Oh, nope. Something is very unhappy at this point. Much better. Okay. I just wanted to make it a little bit larger so you guys could see it a little bit easier. Now, again, we mentioned this earlier, but it's worth pointing out again. Look at this coordinate right here. This coordinate right here is 4, 2. And over here, this coordinate is 2, 4. And that's how it works with a function its inverse. Any coordinate on one of its graphs, you should be able to reverse it, and that coordinate should be on the other graph. Now, it turns out the other thing that that you might notice is if you graph the line y equals x, if you graph the line y equals x, these two graphs are equidistant from it. So if I draw this distance in and this distance, those distances are the same. This distance here is d1, this distance here is d1. Same thing if I pick this coordinate and this coordinate. They're the same distance away from y equals x. In other words, these two graphs are reflections of each other over the line y equals x. So notice that f and its inverse are reflections of each other over the line y equals x. It turns out that's always going to be true for any function and its inverse. If you were to fold right here along this line, if you were to fold right there along y equals x, those graphs should match up perfectly. Now they wouldn't when you do it by hand, but if you did it on a computer, they should match up perfectly. Computers can be highly more accurate. But the point here is that this will always be true. So how are the graphs of f and its inverse related? So the graphs of any function f and its inverse will always be reflections of each other over the line y equals x. Now, why do we care? Well, I would argue it would be, this is a very easy way to look at graphs and know if they're definitely not inverses of each other. So for example, let's say you're looking at two graphs. Let's say you're looking at one graph. Let's say you're looking at one graph that looks like this. Let's say that's f. And then let's say you have another graph that looks like this. That's g. Well, those are clearly not reflections over y equals x. If I draw in y equals x and fold the graph, fold the coordinate plane, those aren't going to match up. F and g aren't going to match up. They're not going to fold over on top of each other. So f and g are clearly not inverses of each other. So I mean, I can just tell that by looking at it. I don't have to do any work. It's like, oh man, those aren't going to be inverses of each other. Whereas if I have, let's say that's f, and let's say that's g. Ooh, well, again, my hand drawing's not perfect, but I would look at that and say f and g might be inverses. Because if I were to fold the graph along y equals x, they might match up. Again, if I actually took some time and care in my graphing of these lines, it would look a little bit better. But you get the idea that this unique aspect of their graphs could help you automatically rule out that they're inverses, or maybe allow for the possibility of them being inverses. Okay, well now it brings us to this idea of a one-to-one function. So here's the thing. let's say you have a function. Let's say you have a function f. Let's say we have a quadratic. It looks like this. This is f. Well, its inverse would be a reflection over the line y equals x, right? So I should be able to fold the xy plane, and then this, if I fold, remember I'm folding over this line right here, right? So I'm going to fold right here. So then this would come down here. So this would be the inverse of f. Again, not perfect because I'm not a computer. But if you look at that red graph, it's not a function. However, it is not a function of x. So what I'm showing you here is every function that you graph has an inverse, but they're not always functions themselves. Okay, so every function of x has an inverse. However, not all such inverses are functions of x themselves. This clearly fails. This fails the vertical line test. That red graph fails the vertical line test. So it's not a function of x. So in mathematics, we like to know ahead of time if the inverse is going to be a function of x. So I don't want to have to graph the inverse before I know if it's a function of x. I'd like to know ahead of time. So we can determine if a particular function of x has an inverse that will also be a function of x by using the horizontal line test. So let's say I have a function f that looks like this. Let's say that's f. Well, if I draw vertical lines anywhere, I'm going to hit the graph one and only one time. That's how I know it's a function of x. That's a done deal. But will its inverse be a function? Well, the way I can check is I draw a horizontal line, and if I hit that graph more than one time, its inverse is not going to be a function. So, for example, if I draw right here, I draw that horizontal line, I hit the graph twice. I'd hit it 3 times, so it doesn't matter. I just hit it twice. That's good enough. So f has an inverse that is not a function of x. So it has an inverse. It definitely has an inverse, but not one that's a function of x. Whereas if I were to draw, say, something like this, let's call that function g. No matter where I draw a horizontal line, I always hit the graph one and only one time. So g has an inverse that is a function of x. Now, this isn't a proof or anything, but why does this work? Well, let's think about it. Any vertical line that I draw here to check if the original one is a function of x, when I flip it over to create the graph of the inverse, those vertical lines would become horizontal lines down here. So we just want to do that backwards. So the idea is this. The horizontal line test is basically saying, look, if I draw a horizontal line here, it'll be a vertical line on the inverse when I flip it over the line y equals x. So if this horizontal line hits the graph more than once, then when I flip it over to create the inverse, it'll hit the graph more than once. So I simply just need to check horizontal lines on the original, which is automatically checking vertical lines on the inverse. Well, that brings us to a definition. So the horizontal line test can be used to determine if a function is one-to-one. So what is a one-to-one function? It's a function where every output is paired with exactly one input. So what's a little sneaky about this definition is it starts out by saying it's a function. So every input is paired with exactly one output. That's a given. But a one-to-one function goes on to say that every output is paired with exactly one input. So I'm going to go ahead and use x's and y's and give you another way to think about this, even though not all functions use x's and y's. I'm going to go ahead and use x's and y's. So another way to think about this is every x is paired with exactly one y, and each y is paired with exactly one x. So for example, parabolas are not one-to-one. So if you draw any parabola, it doesn't matter. Any parabola you draw is not one-to-one, because let's say you have this y value right here of 2. So this y value of 2 is paired with two different x values. This y value of 2 might be paired with -1, and it might be paired with -3. So this function is not one-to-one. We usually abbreviate it with just one-to-one instead of writing out the word one, because y equals negative or positive 2, sorry, -2 there. Y equals +2 is paired with more than one x value. You can see it right here by drawing a horizontal line. So draw a horizontal line, you hit the graph twice. So that is not a one-to-one function. Whereas exponential functions, for example, are one-to-one. So an exponential function is one-to-one. So let's say you have exponential growth. This is one-to-one. So let's say this function is f. F is one-to-one. Because every y, so say you pick this y value, it's paired with just this one x value. So this y value here, y1, is paired with x1, and it's not paired with anything else. Each x is married to one y, and each y is married to that one x. It's a monogamous relationship. And that's true for every single point on that graph. Now, why do I care? Right here. The horizontal line test checks to see if the inverse is a function or not. So let's put all this together. Give an example of a function that is one-to-one, would pass the horizontal line test, and explain why it's one-to-one. So we just drew exponential growth. Let's do exponential decay. Let's do exponential decay. That'll be one-to-one. So if you have exponential decay, so the graph of f passes the horizontal line test, and therefore is a one-to-one function. Since f is one-to-one, its inverse is also a function of x. That's what's important here is I can draw any horizontal line I want. I'm going to hit the graph one and only one time. That means its inverse will be a function. So the thought process goes like this. Passes the horizontal line test, therefore it's one-to-one. Because it's one-to-one, its inverse will be a function of x. But there's lots of functions that are not. There's lots. So for example, you might have a rational function that looks like this. Maybe you have a rational function that looks like this. This is not one-to-one, right? If I draw this horizontal line right there, I hit the graph more than once. I hit the graph right there, and I hit the graph right there. So it's not one-to-one. So let's call this, we can also call this f, it doesn't matter. It's a different example. So this function, f, fails the horizontal line test, which means f is not one-to-one, and therefore its inverse is not a function of x. Again, it's kind of the whole idea, is we'd like to know ahead of time if the inverse is going to be a function or not, function of x or not. All right, so if you have a function, how do you find its inverse? Well, it's kind of been staring us in the face the whole time. The domain becomes the range, and the range becomes the domain. All the x values on the original become y values on the inverse, and all the y values on the original become x values on the inverse. So to find the inverse, the answer is kind of right there. First, write the given function using x and y notation. Or xy notation, however you want to, maybe that's how we should have worded it. Just say using xy notation. Basically, if it's written with function notation, use x's and y's instead. It makes it a little bit easier. And then now we want all the x's to become y's and all the y's to become x's. So replace each x with a y and each y with an x. and then solve for y, and then write using function notation. So basically all we're going to do is exactly what we said earlier. We're going to make sure that every x value becomes a y and every y becomes an x, and that's your inverse. I mean, that's what they are. The domain becomes the range becomes the domain. So let's give it a try. So let's find the inverse of 5 minus x over 3x plus 2. So here's the original. My original function is y equals 5 minus x over 3x plus 2. Its domain, x cannot be negative 2/3, because that would make the denominator 0. Its range, well, let's see. It's improper, so long division. If I long divide, I'm going to get negative 1/3. So I'm going to have a horizontal asymptote at negative 1/3. Now, I don't think you can intersect that horizontal asymptote, but let's check real quick. So will this function ever cross its vertical or its horizontal asymptote? We're going to get negative 3x plus 15 equals negative 3x minus 2. So 15 equals negative 2. No, it can't. Okay. So that means that the range will be all real numbers except negative 1/3, because the graph is just going to follow along negative 1/3 as it gets away from the origin, but never cross it. So that y value will never be in the range. Now, what about its inverse? How do I find its inverse? So the inverse is just simply x equals 5 minus y, 3y plus 2. That's the inverse. It's right there. The moment you put an x where there was a y and a y where there was an x, you've created the inverse. That is the inverse. However, we like to have y by itself. We like to have y equals everything with x. So we're going to go ahead and solve this for y. So I'm going to cross multiply. And then I'm going to add y to both sides and subtract 2x from both sides. I want to get all the y's together so I can factor it out. So I get y equals 5 minus 2x over 3x plus 1. So that's the inverse. Well, the original function was called f, so I'm going to, now I know how to write using function notation, it'd be the inverse of f. And then I want its domain and range, but look, I don't have to do any work. I don't have to do any work. The original range is now this thing's domain. All the y's became the x's, so it's x such that x can't be negative 1/3. And then I don't have to do any work for the range because the original domain is now this one's range. The original x's became the outputs over here, so y can't be negative 2/3. So once you find the inverse, you don't have to do any work to find its domain and range. The original domain becomes this one's range, and the original range becomes this one's domain. All the x's became y's, and the y's became x's. That's the whole idea. That's what's behind the scenes going on for every function and its inverse. Let's do another one. Now notice the way that the example is written. They're telling us that the inverse is going to be a function. Because it says find the inverse function. So it's making it a little bit easier for us, but normally you'd want to check if it's 1-to-1. So for example, on this one, my original is y equals the principal square root of 2x minus 3. If I were to graph that, we know from earlier how to graph this, or at least get a rough sketch. We know that it's the principal square root function, but it's been shifted to the right because it's minus 3, and it's got a horizontal stretch, I believe, right? Because you can, no, that'd be a little bit more bigger than 1. So it's going to be shifted to the right. Like if I were to factor out a 2, so we see that I'm going to shift it to the right, and then it's got a vertical stretch of the square root of 2 applied to it. So basically, the graph would look something like this. This is the original f. And it's going to pass the horizontal line test. So its inverse is going to be a function. Now, the example already told me the inverse was going to be a function because it says find the inverse function of that. But if you had to check it yourself, you could do it real quick. Well, what's the original domain? Well, the radicand is 2x minus 3. So 2x minus 3 can't be negative. So x has to be greater than or equal to 3 halves. The original range, well, y is simply the output of a principal square root. And the output of a principal square root is always a non-negative number. So y has to be greater than or equal to 0. So when I go to find the inverse, let's go find the inverse. X has to equal the principal square root of 2y minus 3. I put x's where there was a y, and I put y's where there was an x. But then I need to solve for y. So I'm going to square both sides. Then I'm going to add 3 to both sides, and then multiply everything by a half. The original was called f, so I'm just going to call this the inverse, because I mean, that is what it is. It's the inverse. And the inverse is a parabola. However, here's where things get a little sneaky. Most parabolas, most quadratic functions have a domain of all real numbers, but not this one, because this one's special. It's the inverse of a radical function. So this one's domain becomes this one's range. And the original range is this one's domain. So it actually does not have a domain of all real numbers like most quadratics. Instead, this one's domain is all non-negative numbers because the original one was a radical function. So if I start out with a function that looks like this, when I go to find its inverse can't have a completely different shape. Remember, it's just that same graph flipped over y equals x. So the inverse has to look something like this, right? It's got to have the same shape but flipped over y equals x. So it can't be the whole parabola. That just wouldn't make sense. So that's a little sneaky. That's a little sneaky. So here we go. Here's the domain, range, and the inverse, which I guess we didn't do that up here. Here's the domain and range and the inverse right there. Okay, so that's it for the most part. Again, be careful when looking at two things and trying to decide if they're going to be inverses of each other or not. So be careful. If I give you f of x is equal to x squared and g of x is equal to the square root of x, you might think, oh, those are definitely inverses of each other, but that would be false. If I plug g into f, I get square root of x squared, which is going to be x. Right? Keep in mind that x is greater than or equal to 0 for that whole thing, because I started with the square root of x, and x can't be negative. If I reverse it, I get square root of x squared. Oops, sorry. I get square root of x squared, which is the absolute value of x. And since I'm starting with x squared, x can be any real number. So these are not, so g of f of x simplifies to the absolute value of x. It doesn't simplify to x. So since this is not just simply x, then they're not inverses of each other. So f and g are not inverses of each other, even though you look at them and think they should be, right? Squaring something and square rooting it, that's inverses. They're not inverses of each other. If you were to graph them, you can see that they're not, right? Here's x squared. Here's square root of x. If I fold one over on top of the other, they don't match up perfectly. I'm missing half the other one. So you got to be careful. Now, I can make these be inverses of each other. I can make them be. So all I have to do is say that for x squared, I only want x greater than 0, or z equal to 0. It's fine too. That changes everything. So now I don't have this half of the parabola. I just have this half of the parabola. Now they are inverses of each other. Down here, since x has to be positive, the square root of x squared is just simply x. Now they both do output x. So I can make them be inverses of each other, but I have to adjust them myself. So if I just take x squared as it normally is, well, then that's not, x squared and the principal square root of x are not inverses of each other. So we gotta be careful.